We are still on number 51, and we're on part B, and we're adding a small wrinkle to this problem. We don't have a molarity given to us. We have a number of grams of a substance, strontium fluoride, given to us within 100 mils only. Then, of course, we are, well, not of course, but we are at back to 25 degrees Celsius. So the first thing we have to do is get this into a molarity of this substance. In doing so, we will say there's 1.1 times 10 to the negative 2 grams strontium fluoride. We will multiply that times, well, actually in this case, divide it by the molar mass, which is 125.62 grams per mole. And that'll give us a value of 8.76 times 10 to the negative 5 moles. If I divide that by the total volume, which is 0.1 liters, that'll give me 8.76 times 10 to negative 4 molarity. And again, that is of strontium fluoride. So looking at the equation of how strontium fluoride would behave, it is a solid. And when it goes into solution, you would get some strontium ions, it's 2 plus, and you would get 2 fluoride ions. So I think it's a good idea to kind of go through this process to kind of road map your way through it. The KSP for this particular substance would look like this. Or when you're putting it in, like as far as how much of these two things you would have there, for every one part of this, you would have this. So for example, this is X and this is 2X. Notice I am distinguishing between the two. I just feel really cautious about putting a 2 up here. Now I do actually interject it into this equation, but as a result, you end up with 4x cubed for that. And as long as I know what strontium is, I know what strontium fluoride is, excuse me, I know what strontium is, and then I can apply it to the whole equation. It's 4x cubed. So I can do that and find that x, in this particular example, will be equal to 2.7 times 10 to the negative 9. And that would be the calculated solubility product, so the KSP for strontium fluoride. All right, part C. We know the KSP for barium iodate, say that 3 times fast, at 25 degrees Celsius is this value. What is the molar solubility of it? So we're going in reverse again for this particular problem. I'm just road mapping my way through here again. 6.0 times 10 to negative 10. I happen to know based on the previous problem how this behaves. Maybe I'm stepping ahead here a little bit. And again, based on how these guys are going to behave, it's x and 2x for them. So if I know what this value is and I have this equation, I can simply just do the algebra on this and solve for what x is. And if I do that, x will be equal to 5.31 times 10 to the negative 4, and that is a molarity. And that is what is equal to barium, which is x, which happens to have the same stoichiometric relationship to barium iodate. That's it. All right, let's bounce over to just a little bit more notes, and then we'll keep on pushing into these last couple of homework problems. All right, so we're going to add another wrinkle to this. Calculate the effect of a common ion on solubility. So specifically, calculate solubility of calcium fluoride again, that is 0.01 molarity in calcium nitrate. And then we'll do a separate problem, which I'll introduce shortly. So we know what the KSB was. We did that in the previous problem, or 2. This is at 25 degrees Celsius, 3.9 times 10 to the negative 11. Okay, so because we have some extra stuff going on here, we are going to make a rice table. It is calcium fluoride. And I do know how much this is. Initially, I don't have any of this, but when the calcium fluoride goes into solution, it's going to produce 1 part of this and 2 parts of that. And I am going to write down as far as the value for this. I'm not going to say it's insignificant. It's right there. So we are going to add some X amount to it, but we'll come back around. At the moment, I may decide to get rid of that. I think I will. So having this amount here, I'm trying to solve again for what X is. So let me kind of continue this roadmap, putting this together. Calcium ions and some fluoride ions. And putting these in here, I'm going to plug in the KSB because I do know what that is. And as far as how much, based on how the previous problems have been going, as far as what X is, it's pretty small. And I'm going to continue to make that assumption in the math here. If you wanted to go ahead and use like a quadratic or something, help yourself. But I'm just telling you it's insignificant compared to how large, relatively, that value is in comparison to it. So I'll leave that in. This is 2x, and it will be squared. And if we go ahead and just do the algebra here and solve for it, bring this over, square this out, and of course divide through, x will be equal to 3.1 times 10 to the negative 5. And again, this is the amounts of, with having a common ion present. So which is interesting. Just as I'm not going to go through the math. I think we just did as a previous problem though. If I did without having a common ion present, x would have been equal to 2.1 times 10 to the negative 4, which is larger. So it's interesting. So without having a common ion present, the value would have been 2.1 times 10 to the negative 4. With a common ion present, it is something smaller. So again, according to Le Chatelier's principle, this acts as an inhibitor going into solution. All right, let's do the same kind of problem, but instead of adding that concentration of calcium, we'll add that concentration of fluoride. And I'll see if I can squeeze this in here. So I'm going to write that up almost exactly the same, except in this case, I'm going to say 3.9, getting a little bit ahead of myself. So I'm just kind of starting off in this area right here. Calcium, I don't know. So X, and then for the second part, I'm going to say 0.01, and I'm putting the whole thing in here just for a moment. So again, we're still going to assume that X is really small. I'm going to write it down. We assume X is very small, and it was in the previous problem. X is very small. So, whoops, I'll do this. So 2x is still very small. So I can see the equation. I'm just going to ignore this part of it. Of course, I can't ignore the 2 in the exponential part, but it'll become x times 0.1 squared. And if I do the rest of the math here, x will equal to 3.9 times 10 to the negative 7 molarity. Okay, so compare the numbers. This is what I had when I had the calcium, and when I use the exact same concentration, but in place use it for fluoride, it's even smaller, which goes based upon how, even though, again, it's the same value, I'm not doubling it, it just is that value. Here it is. But because of the exponential effect of the fluoride, it is much, much less. Okay. Looks like we are done for this lecture. I think we got one more. No, this is just the example. We'll do one more lecture after this and keep on rolling.